Hi everyone, welcome to the Mini-Astro-workshop series 2020. So today with us we have Manas Vishal, who is currently pursuing his masters at IISER Kolkata, and he has been working on LISA, black holes, gravitational waves, etc. a lot in general. And currently he is majorly working on ADS black holes, anti-T black holes. Uh, and wherein he's actually looking at ADS spacetimes and massless scalar field equations that are associated with ADS metric. And he is also currently doing a small independent study on magnetohydrodynamics and fluid mechanics. As you all may have heard from the previous talk, magnetohydrodynamics are a set of equations involving Maxwell's equation and Euler fluid equations, which are crucial to model and understand complex astrophysical systems. And he has also recently done, I think he's also continuing to work as a part of his summer internship at University of Massachusetts Dartmouth, where he worked with Professor Gaurav Khanna and Scott Field on EMRI, extreme mass ratio in spiral surrogate modeling. So the thing is, using numerical relativity simulations, one actually needs a high performance computing and a lot of resources and a lot of time to compute any usable gravitational waveform to detect or do parameter estimation, which you may have heard in the previous talks. But this surrogate modeling is something that's upcoming, which can actually be used to fasten this generation of gravitational waveforms, and especially as the LISA is an upcoming detector, which Manas is going to talk about later, which actually mainly detects something called an extreme mass ratio in spiral system, which again Manas is going to talk about. And for that particular system, there are no currently very accurate and a lot of waveforms. And towards that, he has been working on making a surrogate modeling. And even if there is a surrogate model to make faster and more waveforms, no one has ever included the spin and looked at curved black holes in general. But he's been working on that to involve spin in his system and look at its effects and construct better, accurate, and large number of waveforms. And apart from this, he has also worked on the LISA experiment itself, like modeling it, like one understanding the orbital dynamics of LISA. Uh, in the other was using a software called Finus, if I understand correctly, which is actually more catered towards students so that they can understand how the LISA works and what are all the noises and different noises that are involved in the LISA experiment. And uh, he has also like studied a lot of general relativity, cosmology, and dark matter a lot in his during his undergrad and masters. And uh, he has also received two awards, one by Inspire Award by DST, and the other was KYPY. As you all know, the famous KYPY scholarship that's given for people to pursue their basic research in basic sciences. And using that, he's currently doing his masters at IISER Kolkata, as I previously mentioned. And I think he's in his final year, and he'll be switching to a PhD soon, and will be working more on black holes, gravitational waves, etc. So I'm very glad that he's here and he can talk about EMRI, circuit modeling, LISA, etc. in general, as it's something that people should really look forward to. It's like the next LIGO, the next big thing that's going to revolutionize the way we look at the universe. I'm very happy that Manas agreed to talk about that.
Yeah.
Manas, up to you.
Thank you, Surendra, for this wonderful introduction. Okay, so there is one slight correction in the finesse part. Finesse actually helps in modeling the LIGO and A-LIGO interferometers. So what it does is like you have this, it's a wrapper basically of Python, and you can introduce the noise budgets and get the sensitivity curve of different types of interferometer using that. Just a slight correction. Okay. So yeah, let's get started now. I am Vishal, as introduced by Surendra. I will be talking about LISA and the orbital dynamics of it, and what are its primary sources of gravitational waves. I must give you a slight notification that I get nervous and I tend to speak very fast. So please stop me when I get up to that pace. Okay, let's get started. So LISA stands for Laser Interferometer Space Antenna. As you all know that gravitational waves have been detected already in 2015 by LIGO. So LIGO is basically an array of two detectors which are like in perpendicular direction, like Michelson interferometer. So LISA is our upcoming space-borne detector, which will have a 3 spacecrafts. Can you see my pointer? Okay, I'm assuming that you can see my pointer.
Yeah, we can.
So yeah, so there will be 3 spacecrafts, 1, 2, and 3, and it will be an equilateral formation, equilateral triangle formation, and it will be in a heliocentric orbit around Sun with 20-degree out of phase from Earth. What it means is that if Earth is here, the center of mass will orbit this orbit, and it will be 20-degree away from the Earth. So I will be referring this diagram a lot over the next 15 minutes. I will be breaking my talk into 2 sections. Part 1, where I will be talking about the astrodynamics or the orbital dynamics in specific way. I will be talking how there is a flexing in the arms, the three arms, L1. Suppose you mention it and denote it as L1, L2. So this will be L1, 2, this will be L2, 3, and this will be L1, 3. So basically these are 3 arms of the detector, and these actually flex over time if you have to, if there is 1 year signal, then if the center of mass of this spacecraft arrays are moving, then there will be flexing in the arms of these spacecrafts such that there will be breathing modes. So how do we calculate that? So, okay. So these calculations are done in Clohessy-Wiltshire frame. So this frame is basically just a co-rotating frame in this system. So what we do is that we take the center of mass of these 3 spacecrafts and take the Sun, and we go to a coordinate where we go to a coordinate of center of mass, and then we rotate the center of mass such that these 2 objects are in the rest frame. Okay. So if I can show you this animation. So yeah, so these are 3 spacecrafts which are moving around the Sun, and the angle between them, Earth and the center of mass, is 20-degree. So this is orbit of 1 spacecraft, and after 1 period you can see the orbit of 2nd spacecraft, and after 1 orbit of this you can see the orbit of 3rd spacecraft. So basically these are oriented with each other on an angle of 120-degree. So after 3 rotation you will get the full 360-degree. Okay. And these are the breathing modes. These are the breathing modes. What happens is basically there is a flexing. So flexing, if you mean, is like the length of the arm changes over time. Suppose this is L23 distance, the distance between 2nd and 3rd spacecraft. The proposed distance, this is from the paper way back in 2005. At that time, the proposed distance of the LISA spacecraft was to be 5 million kilometers, but now it's 2.5 million kilometers. So there's one more option for you to work on these new calculations, and you can show that there will be the same flexing, but the values will be different. Okay, so let us consider this solid line. So this is the distance, the variation of the distance over an year. You can see that after 6 months, the flexing increases after decreases and then increases after in the rest quarter of the year. So these are called the breathing modes. This happens not only with the this happens with the other two lengths as well. Okay. So what we do is we introduce a slight tilt in the orbital plane of the LISA. If you remember the figure from the first slide, I had shown, okay, maybe I could show you this once more. So yeah, if you see that this plane of the equilateral plane of the three spacecrafts are tilted to an angle of 60 degrees. It's not perpendicular to the orbit of the Earth. So we include a delta parameter such that we can change it and then see the effect of this perturbation and the flexing of the arms of the LISA. So if you can see the figure clearly, so the angle is actually 60 degrees and we have introduced the delta parameter. So now we plot, we calculate the flexing of the arms with the function as a function of delta, and then we plot it in 3D and 2D as well. So if you consider a distance, suppose L2 3, and you calculate the distance between the two spacecrafts and then plot it with the varying delta, then you can see that there is a reduction the flexing of the arms. So there is the breathing modes are decreased. So basically, why do you want this? Is you want the interferometer to have a constant difference between the arm, which can be calculated theoretically, such that you know how much there is the you know that there will be a strain caused by the gravitational waves if the gravitational wave passes through a interferometer. So we want it to be as much as constant it can be. So we plot it and we find an optimal parameter such that the flexing is or the breathing modes are reduced to a great significance. So yeah, so we find that for a delta equals to 0.0118, we get a good reduction of flexing up to a factor of 2.4. So we have also plotted a relative distance or the difference between two arms and the time of the time between the time. So what we see is that in if we introduce a delta parameter of 5/8, which was equals to 0.0118, we get a region where it's almost constant. So we can operate the LISA in this region and we can get a good data from gravitational wave strain. So we can see that by introducing a slight tilting in the plane of spacecraft, we actually reduce the flexing by a factor of 2.4. This means a lot because we have the arm's length in the order of 10 to the power 6 kilometers. So if you reduce it to a factor of like 115,000 kilometers to 48,000 kilometers, that means a lot when you are talking about astronomical distances. So if we consider the Doppler shift as well, the reduction factor can also be reduced up to the value of 6. So we can now move on to part 2 of our talk. So I will be talking about the primary sources of LISA, which are extreme mass ratio in spirals. LISA is actually sensible in the range of few millihertz to a few hertz. In this region, you can see our noise budget lies in the range of extreme mass ratio in spirals, massive binaries, and galactic binaries in spirals. Whereas in LIGO is sensitive towards higher end of the spectrum of frequency, and the pulsar timing array, international pulsar timing array, is sensitive towards a lower value of frequency. It is sensitive towards stochastic background or the gravitational cosmic background. These are the same thing. And extreme mass ratio in spirals are basically what we consider as if you have the ratio of the two black holes, the masses of the two black holes, the ratio should lie between 3, and it can go up to infinity as well. Or basically we consider for our models, we consider it up to 10 to power 6 or 10 million. Okay, so sorry, 1 million. And we basically, for this extreme mass ratio in spirals, we can assume a curve, assume a background. You might, I guess you might all know about general relativity up to this by the talks. So we assume a metric or the background in which there is a perturbation by the smaller black hole. And the smaller black hole, the problem lies with the smaller black hole, as you have to model it numerically accurately enough such that you can get a good result from that model. So what we do is, generally in numerical relativity, we use a delta function to represent a smaller black hole, but it doesn't have any spin. And also primary black hole can be of any geometry like Schwarzschild, Kerr, or Kerr-Newman, and it can also have different types of rotations or spin, which we call it. There are different ways to do black hole perturbation theory. You can use either Tucholsky formalism or BSSN formalism. So I have used Tucholsky formalism because it helps us to model the system accurately when you have different types of spin and different type of fields. Fields as in you have different types of field as in like electromagnetic field and gravity field. It also helps us to couple different type of modes, which are the harmonics of the spherical or the spheroidal harmonics, spin weighted harmonics. That's why we have used Tucholsky formalism. So basically this plot shows us like what region will be the what theory will be the best in what region. So on y-axis we have the separation between two black holes, and on x-axis we have the mass ratio of the two black holes. You can see for a ratio up to 3 or 10, numerical relativity works best. And for separation, if we are separated, the black holes are separated, or they are going to merge, or they have started to experience the field of other black hole, we can use post-Newtonian or the expansion methods of Minkowskian methods as well. But if you have something like you have a massive black hole, and then you have a smaller black hole lying around it and rotating around it, then you will have to use perturbation theory or self-force methods. So perturbation theory, as I explained, you consider this black hole as a delta function, and you consider this black hole as the background space-time. This can be spinning, and this can also be spinning, but no one has yet worked on the spinning secondary black holes. This can be done, but you will have to consider higher derivatives of delta functions. So our final goal is to solve basically a wave equation. As you already know, gravitational waves are waves. So they are traveling at the speed of light. So they obey this relation, which is like the double dots represent the derivative in different coordinates, and the prime this is time derivative, and these are radial derivatives. We can also have a partial differential equation with a potential term for a more realistic situation. So this potential term will depend on the exact radial coordinates, and these coordinates, the derivatives are in the different tortoise coordinates. Those are just nomenclature, and then that can be done very easily, but by just a substitution. And there can also be a moving delta function which will represent the source function or the secondary black hole in the RHS. We have a different, I have actually got a final master equation, but I can't actually show that. So in that, you can also have a coupling between different wave equation solution, such that suppose you have a solution, this solution for L equal to 0 mode, this L equal to 0 mode will also feed back to L equal to 2 mode or other higher modes. And then you can solve this, the coupled differential equation, and then get a full solution of gravitational waves. Okay, so the problem lies ahead is that how do you represent the derivatives in different types of algorithms? In you might know about the finite difference techniques. In finite difference techniques, you basically consider discretize the system, the derivatives, into a grid, a known grid. But finite difference techniques have been known for like 50 or actually 200 years. Newton actually discovered that. You might know about the you have this suppose you have a grid and you have to find the estimate of the future function. You just do fx plus 1 equals to slope of the difference between the value of the y and divided by the x values, the grid spacing, and then you multiply it with the future x value. Then you get a future value. But these problems are well known because a lot of people have already worked on shocks and how the flux reconstruction method, such that you can get a smooth solution out of it. But the problem is, if you sometimes you might not get a smooth solution, and you have to evolve the differential equations over multiple time scales, such that you can get a different physics out of it. So some phenomenon can have different time scales. It can require a small, in very small short time, it can evolve to a different system. And some physics might require a long-term evolution of the system, such that you can get a, you can actually infer something good physics out of it. You can also have like change of geometry, like you can have two systems merging around, like neutron star mergers, black hole mergers. There can also be supernova explosions. There can also be different types of multi-physics system, like you have neutron star systems, binary neutron star system. You have to implement GR, general relativity, hydrodynamics, magnetohydrodynamics, and you will also have to deal with the nuclear reaction and neutrinos or photons as well. So that's why these are the difficulties which are not actually solvable by finite difference techniques. So we use a different type of technique called discontinuous Galerkin method. This method is basically a hybrid method of finite difference and finite element methods. What we basically do is, in finite difference techniques, you have a grid, then you discretize the grid equally, such that you the spacing is equal, and you have to, like suppose you want to find this value. So what we do is, like, you take this value, you discretize the system, use the difference and use the future value of x, and estimate using the previous values. But you might get into trouble when you want to calculate the values at the endpoints. You can use different types of techniques in finite differences, like central difference, or you can use the forward Euler method. But you always get into trouble when you want to calculate the boundary values of the grid. You will also have to deal with the coefficients, which are basically which basically comes from the Taylor expansion. As you already know that the finite difference method are basically the reduced form of Taylor expansion with an order with you have to consider the big O notation of 2, 3, or 4 or higher orders. But in spectral method, what we do is, like, we assign the grid such that there is no equal spacing between them. You cluster the grid around the endpoints, and then you do the different finite element methods. such that you can get a good value of at the endpoints. But in DG method, what we do is we define a grid, and the grid is unstructured totally. And for 1D system, we use basically lines, and we divide into different line segments. And for 2D systems, we use triangles, and for 3D system, we use tetrahedrons. So, okay. So basically, this is a sample grid, and these are the notation for the grid. So this is the, suppose you want to consider a grid, suppose consider this subdomains actually. So this is a subdomain, and you divide the whole grid into different subdomains like this, and you ensure that the rightmost part of this previous domain and the leftmost part of this domain must be equal, such that you get a smooth grid. So, and the local solution in this grid, which will be evaluated as the summation of the local basis of the polynomials of degree at most n. So suppose you have some solution, something like looking like this. Okay, I have a better figure. Okay. So you can estimate this value by using some polynomials, or like suppose you want to use some polynomials y equals to x. Then you can have a straight line passing through this grid, and you will have to ensure that this grid is smooth and the solution can be discontinuous. Okay, and then the global solution will be given as a direct sum of the entire subdomain. Okay, what this means is basically, suppose you have a solution such that this is x square, the local solution is given as x square, and the local solution in this grid is given as x. So what we basically do is we add them up separately, such that the global solution will be x square and x in this region and rest in 0. So finite volume or difference methods are basically, if you consider a cell average of the system. Okay, so what it basically means is that in finite difference techniques, you only pass a constant value to the grid. Suppose the green, I guess you can see this green function. So basically what this green line or curve is representing is our analytic solution, which is our true solution. And these are our numerical solutions. In finite volume or finite difference methods, we basically estimate this function, this analytic function, using a numerical function, which is the cell average of the function. Or basically, it is constant all over the subdomain, in this subdomain. And for this subdomain, this is represented by this constant value. And for this subdomain, this is represented by this constant value. In FD methods or finite difference methods, the work have already been, several works have already been done to join these solutions such that you get a smooth solution out of it. And flux reconstruction method, or basically what flux reconstruction method mean is that you pass the information from this grid to this grid, such that, or two adjacent grids, such that you can join this solution and you can get a smooth solution. But you want the finite difference techniques to be as smooth as possible, you will have to use a wider extension, or basically wider grid, such that, and you will have to divide the grid into smaller points, such that you will get you can estimate it up to a linear order. Or basically, if you want to increase the grid number of grids, the error will decrease as the order of -2. Okay, or goes down by the polynomially. But in DG method, the error goes down exponentially. So in basically in DG method, suppose you have this grid, we want to do is like this. We are taking the artistic freedom and choosing this, separating this equal grid, but these values are the same, and we are separating them. Why we are doing this is because we have to represent a delta function as well. Okay, so As I already told you, like usually denote our delta function or the secondary black hole as a delta function of x. So suppose you have a simple hyperbolic PDE offered with a delta source term, and the speed of the equation is speed of the information traveling is given by c, which is equal to speed of light. Then you can have this equation, and this delta function will only come up as in our DG scheme as an extra flux to this model. Flux is basically the information passed between two grids. Suppose you have this a solution over here, and suppose you have a solution over here, the local solution, and you want this information to be passed such that this grid knows what has happened before in my grid, so that I can evolve my wave equation, and I can get a full good approximation of our our analytical solution. So this value will be added to the flux which is being passed earlier. If you don't have a delta function, there will be no extra term in the flux which is being passed from this point to this point. But if you have a delta function which is represented by a black hole, which represents a black hole, this term, this extra term CGT, GT basically means how the delta function is behaving with respect to time. You can have a delta function which can be moving, and this will represent the movement of the source term with respect to time. Okay, so our algorithm or our scheme depends on the error of our scheme falls off exponentially because we want a smooth solution, and the error this is the basically error. You are subtracting the analytical solution from the numerical solution and over the subdomains dk, and then you will get a relationship which is directly proportional to the size of the domain exponentially, and n is the degree of the polynomial which you have used. But there is a plot. You can see that I have plotted the number of the subdomains, and I have used n equals to 5. So basically I'm using degree 5 polynomial to estimate my solution. I will be showing you like how to run these simulations in my tutorials. So I have plotted the error plot and the number of the subdomains. You can see the slope of the curve or the log plot. So basically what you do is you take a log here. You can see the slope will be n plus 1 for the size of domains, but minus n plus 1 for the number of domains. So I have gotten a slope of minus 5.5, which is a very good convergence rate as compared to other methods. The error is falling exponentially. Okay, so I guess my theoretical part is over by now. We can move to the tutorial part. If you have any questions, please, you can ask me now.
Yeah, before that, if people have any questions, they can either raise their hand or post a question to the chat. So maybe Manas, you can try to. Okay, Liz has a question. Yeah. Please.
Yeah, so basically this whole process, was it like this, all the mathematics that we were doing, was this all process to find out the source, and like
so, yeah,
where
I
it
think I might
actually
not
is?
have been clear. I guess this basically you have to solve the wave equation for the source modeling or the delta term. You have already had the delta term. So you have the mass of the black hole and the secondary black hole, the second black hole, which will be represented as a point particle. And how do you represent the point particle in DG method? That's what I have shown here. Okay, let me show. So this delta function, which will be the source term, this represents the second black hole, and the first black hole, which is the massive black hole, which will represent the background of the space-time. This if you want to calculate the wave equation, you will have to deal with the you will have to calculate it from the Tucholsky equation, which I don't think I could cover in this talk. That's why I have left it. I've only showed how can you model the wave equation, or how can you solve the wave equation using DG scheme, the discontinuous Galerkin scheme. Was that clear, Dwij?
So basically just solving the wave equation, right?
Yeah, yeah.
Okay, then I got it. Thank you.
So yeah, wave for more realistic case, in like in two black holes merging case, the wave equation will have a different terms such that there will be a potential and there will be a coupling between different types of modes in them. Okay, yeah. So for a realistic case, you will have this type of equation and coupled with different types of these equation as well.
Okay, any more questions?
Okay. Pratyush, I have totally lost track of as of what's going on. What are we trying to do?
I think maybe Manas, you could try to reiterate the physical system that we're trying to solve and why that old methods may not work here. I think you can try to reiterate that.
Okay. So we can use this. Sorry. So we are basically seeing here like why we need DG method, because we want the this our code to run for a longer time and very fastly. We want it to be parallelizable because we want to run it in a supercomputer, a cluster, and DG method is self-parallelizable because you can already have discretized the system over subdomains. So you can assign this, suppose this is a grid we are talking about, and you can assign this grid to a processor and this grid to a different processor, and you won't have to, you will have to only communicate the flux passing between this adjacent grids. So, but in finite difference techniques, the that method is not parallelizable that much as compared to DG method. And the problem which we are looking into it is extreme mass restraint spirals, where you have a massive black hole. Wait a minute. Where you have a massive black hole, and then you have a second black hole which is revolving around the system, and then it will finally merge and give you a remnant, or basically there will be another black hole after the merger. So basically we want this the strain, or the we want the perturbation in space-time. We want to get that perturbation in space-time, because LISA will be detecting that, and that is represented by the wave equation which I have shown you. So yeah, so we are tackling that problem.
Manas, if you remember, there has been a recent video by RIT showing a video of 128 mass ratio.
Yeah.
You remember that, right? Maybe
yeah.
We could try to show that. Then people.
Yeah, I can open it in the parallel tab.
Yeah.
Okay.
Meanwhile, when he's trying to, you can post your questions or raise your hand. So to add what Manas was trying to say, like usually when you're using what LIGO or advanced LIGO detects is two black holes which have the mass of almost same. But when you're going to LISA, like usually associated with these two equal mass black holes, you have a gravitation wave, right? And that particular gravitation wave will have certain frequencies since it's a wave. So using LIGO, you can only detect waves in a certain range, starting from 10 hertz to some 1 kilohertz. But once you go below 10 hertz or go above 1 kilohertz, LIGO is not sensitive and the noise will dominate. You can't really detect. So But there are also sources out there in the universe, apart from these two equal mass binary black holes, like the one here Manas showed in the plot on the right bottom, where you have a very small black hole and a very large black hole. So these type of systems can actually be found usually around the galaxy centers, where you have your supermassive black hole sitting, and you have other tiny black holes which are revolving around each other, and even they would produce some gravitational waves, right? So the frequency associated with such gravitational waves is very small. They are in the range of millihertz, like even below 10 hertz. Then obviously they can't be detected by LIGO, so they will be detected by LISA. But such sources are, there are so many sources like that, that we predict a lot of such events happening, such sources being present, and so many gravitational waves being detected. One has to develop a template bank. If you all have remembered the previous talks on gravitational waves, data analysis, etc. So to produce all these waveforms, the old conventional way, as rightly pointed by Manas, is numerical relativity. But unfortunately, one can't use the conventional numerical relativity ways to solve the resultant equations to get the gravitational waveform associated with such a extreme mass ratio system. So one has to go on using some other, it's a differently entirely physical system, different time scales, different forces, etc., right? And to really parallelize and to produce enough number of gravitational waveforms so that one can make a good detection, DG scheme is something that's really catching up. And Manas was talking about how one can use DG and how good it is compared to finite differencing method, because as he rightly pointed out, DG scheme is already rather discontinuous. Like you can distribute the workload among different processors. So if you all may have known recently, I mean, there's something called Moore's law. Okay, what it basically tells is modern supercomputers can actually perform very well compared to old supercomputers because of parallelization. So the key to running a heavy code very fast and to produce large number of waveforms in short amount of time using less minimum number of resources is to be able to parallelize. And the best way to parallelize the given system and to use minimum resources, etc., is DG scheme.
Yeah, thanks, Surendra.
And Rafia server is asking, are you
Yeah,
using self?
I've used black hole perturbation theory to model EMRIs. So basically, Tucholsky formalism is the way to go. You have the Tucholsky equation, and then you use that Tucholsky equation to reduce it to a different a 1D system, 1 plus 1D actually system, and then you get the wave equation from there. Yeah. So, okay, as Surendra was talking about Moore's law, so I might also point this out, that since you can get a large number of processors, there will be a problem when you want to communicate between two different types of processors. Suppose you want to pass information from one processor different, there will be a delay to that, and your code will not eventually scale up to the number of processors. You might expect that you will get a linear relationship between your the time taken by your code to run and the number of processors you have. But the problem is you have to optimize your code very well such that you can get that relationship. But in DG method, you can have this thing. You have the freedom to use task-based parallelism. So what we do is basically we only assign that the job. It's like first come first serve basis. You take a processor, you assign a job to it, and you assign a job to each processor. Suppose every task will require different amount of time, and if a processor is going to finish its job, then your code will assign the next job to that processor which is going to finish the job. In that way, you can parallelize your code to a great extent. So this is also a way to go by using DG method and using task-based parallelism. Many engineers actually might know DG method by a different name. It's called finite element method. But in finite element method, you want the the solution to be continuous. But in DG method, you don't want the solution to be continuous such that you can handle shocks as well.
Yeah, next, Vish is asking, there was a software known as EMRI which helps in parallelization. What does it do exactly?
I actually don't have any idea about that. Do you have any idea about that?
Yeah, so it's a different way of parallelizing things. So the thing is, yeah, the key thing, I mean, to do that, I have to use some terminology. I'm rather not trying to do that. Um, so mm, it's a better way of implementing something called adaptive mesh refinement. Okay, so adaptive mesh
Oh,
refinement.
this is, I think I know about this. You have this, you distribute the grid where the physics is happening, and it is finally refined into that where the exact physics is happening, and the grid is very coarse when you don't have any actual physics happening. I guess this is the code.
Yeah, that's the key idea. But then it's just that use conventional way of AMR, and this is different. So thing is, supposing you have two black holes and you want to understand what's happening in and around black hole rather than what's happening at far away from black holes in a numerical utility simulation. So you want to resolve your grid and have finer grids around black holes and coarser grids as you move away from the black holes. That's what AMR is, and it's usually based on like you have. I mean, maybe I'm going into too technical. So the thing is, okay. Okay, maybe we'll try to take it at the end. It's a bit
Okay.
technical question. Uh,
So yeah. So okay. Is there any?
so maybe I got the link to the YouTube video. I'll try to share it in the chat and you can display it.
Yeah, I okay.
Okay.
Yeah. Can you see my screen?
No, we still see the slides.
Okay. Now?
Yeah.
So these are the EMRI system. This, okay, let me just pause for a while. Not, okay, yeah. Okay, if you can see that there is this small perturbation in the background space-time. Suppose you have a short shell black hole, which is not rotating. Okay. Okay, yeah, this looks better. Suppose you have a black hole which is not rotating, that is, it is virtual black hole, and there is one smaller black hole which is rotating around it, and this will generate a waveform which will be sensitive to in LISA spectrum or LISA band. This will be detected by LISA, and to model the system, you use black hole perturbation theory. So this background spacetime, which you can see, this fabric, and there's small dent which you can see. This is caused by this small black hole, and this singularity. This is caused by the bigger black hole. So we actually, what we do is in the Kolsky equation, we use this background and we consider this as a delta function, and then we solve that delta function in a wave equation. This will be the source term, and this will be the background stuff, background space-time. That's in that way you can solve the wave equation for gravitational waves. You can see that they are going to merge. The scale of the time is going to change. At t equals to 0, they will merge. And you have these beautiful spherical harmonics. And this is the merger event, and then you have a ring down. I hope this makes more sense.
If people have any more questions, they can either raise their hand or post in the chat. We'll give 30 seconds. Okay, Manas, I think you can continue.
Okay, so I am now going to show you like how you can use DG method in MATLAB. Okay, let me just close the presentation. Okay, so basically, this is the GitHub repo where I will be going to provide all the links in my GitHub page or the folder under day 9. And this is the repository which we'll be following. This repository is created by Tim Warburton, and this is based on the book by Jan Hastaven and Tim Warburton on discontinuous Galerkin methods. So you first of all download it from here, download zip, or you can also use git clone repository, and then you just extract that zip file. So you will have this folder nodal DG master. You will have different types of codes, and you can use these codes to do the discontinuous Galerkin scheme. So we are now in MATLAB, and this is the repository which I was talking about. I'm really sorry. Yeah. So this is the repository which I showed you now, and it has codes 1.1 folder. These are the other folders which will not be needed right now. Okay. 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 Let me just real quick open the folder. So here we now. So the structure, I will be explaining the structure in like 5 minutes, and then I can show you the advection equation. How you can solve that advection equation which I was talking about. So these are the different codes which you have. You can also run different types of Maxwell equation codes, and in 1D and 2D. This has a 3D code as well, but I don't think it has a Maxwell. Okay, it has Maxwell as well. So you can run the solve the Maxwell equation in 3D grid as well. So we are now interested in 1D advection equation. So first of all, what we do is we add the folder to the path and the subfolder as well. And then you have to run this mypath file, which is basically stores the folder structure in your path variable, such that you can run the code, the specific MATLAB file from anywhere if you are in this folder, in this nodal DG master folder. Okay. I hope you can see my screen.
Yeah, we can.
Okay. So yeah, so as you can see, this file only contains something, the grid, the folder structure, and it is adding to a variable such that you will PW, such that you can run the code from anywhere. What we want to do is we want to run this file, and you can see there will be variable created. Okay. This shouldn't have happened. Okay, just give me a minute.
Meanwhile, people can post more questions to the chat.
Is there any upper limit to the mass ratio? Yeah, the problem is we want the mass ratio to between 3 to 10 to the power 6. If any ratio above that, or if you take the inverse ratio, there won't be a significant waveform which can be detected by LISA. The frequency will be very low then. Okay, my folder structure has messed up. Okay, let me just re-extract that zip file.
Yeah, it started.
So yeah, this is the same folder. Basically, my code structure changed. That's why I was not getting I was not able to add to the path. So what we want to do is we run the mypath file by adding this code directly to the path for now, and then we run the mypath file. Okay. So yeah, Murphy's law is correct. Oh, if you want something to go wrong, then it will go wrong. What is this happening? Going to talk about. So this code, this zip file contains different types of codes. So the code which has a driver file in it, you want to run that code because it will contain the initialization of your system, and it will generate the grid. It will you can set the initial condition of your wave the partial differential equation, and you can set the different type of different parameters to pass to be the differential equation. So suppose you want the advection equation to be run in this grid. This is the order of the polynomials which you want to approximate the solution to, and this will generate the grid. And this is the lower limit of the grid of the 1D grid, and this will be the higher limit of the 1D grid. So basically this will generate a grid which is spaced from 0 to 2 with 10 number of subdomains. This will initialize the grid and the metric, and this will you are passing the initial condition by setting the initial value of every subdomain as sin x, and the final time which you want the solution to have will be 10. And then you run this advec 1D code which contains the different types of formalism of DG, and you can see that you are defining the advection speed a equals to 2 pi. For light or gravitational wave, we will have a equals to 1. Okay, and here you are using RK plus DG method. RK is for integration of time and DG is for space. There have been methods which use DG plus DG formalism, but that is not very efficient, or actually does not give you a significant result over DG plus RK4. DG method only works for space discretization, not for time. You have to look for something other than DG for RK for time integration. So basically, here you are integrating the over time, and you are passing the flux, which is the RHSU, which computes the RH right hand side of the U function from this file advec RHS1D. And here you are constructing the flux and passing it to the time integration in advec 1D. And after running this whole 3 codes, you will get the final solution of U stored in U, array of U. So this is the code structure of YANAS7. To solve the wave equation, basically what will we do is reduce the wave equation into 1 plus 1D form, 2 different types of advection equation, two sets of advection equation, and then solve those using coupled equation, that coupled advection equation, and then you can get the final wave equation from there.
Yeah, guys. So any questions, you may raise your hand or post it to the chat.
I'm really sorry if I was not very clear. Uh, I'm not quite experienced in this.
I think maybe just to reiterate what Manas was trying to say, so he's trying to show, I guess, the advection, the simple advection equation rather than the whole wave equation as an example to demonstrate how discontinuous Gallatin method can actually be used to solve the advection equation. And then in the end, he was trying to say how your given wave equation, which is a partial differential equation, can be divided or split into using some different variables into two separate equations which are coupled, and they can be solved, and then the final wave solution to the wave equation can be obtained. So, okay, so Venu is asking, I have a slightly off-track question I want to ask regarding career-related opportunities. I have graduated this year in BSc Physics. I want to pursue research in theoretical physics. Please guide. So maybe let's take this towards the end of the session.
Yeah.
Yeah.
So I will try once more to run through a different folder. Let me see if this works, because I really want to show the discretization of the grid, because that is the gist of this discontinuous Galerkin method.
Maybe you could just copy paste that small mesh grid generation to separate and then make a plot, right?
Yeah, I can do that, but I don't know why is this happening.
Dries has a question. Yeah, Dries, go ahead.
So why exactly do we need Lisa to be at space, you know?
Okay, why do we need
Lisa to be at space.
Lisa to be in space?
Yeah.
Yeah. So we have a different types of projects coming up ahead, like Einstein Telescope and Cosmic Explorer, which will be ground-based detectors, and the arm length will be 40 kilometers, and it will be not on the ground like LIGO and a LIGO. They will be under the ground and around a few 1 kilometer, I guess, and it will be in triangular array. So we want LISA to be in space because we want to reduce the seismic noise, and we actually want the system, the test mass. Basically, what you're doing is like you are passing the wave, the gravitational wave, through a test mass, and then you are checking like how much the strain or how much it has caused the how much the space time by the gravitational wave in that test mass. But if you consider a test mass in the ground or on the ground, then you will have different types of noises coming from, and you want the test mass to be freely floating in the universe. So that's why you want to go to space. I guess that might have answered your question.
Just to add to that, we are interested in a different, so as usual, if you see the electromagnetic spectrum, it has a huge range, right? Ranging from
Yeah.
X-rays, gamma rays, visible, infrared.
And that as well.
So similarly, coming to gravitational waves, it has a huge frequency range, like different sources release gravitational waves at different frequencies. So if you really want to probe the sub-hertz range, which is below 10 hertz, where you want to have length of the arms in your detector to be as huge as possible, so that they can detect these huge gravitational waves, which have wavelengths on the range of some thousands of kilometers, even more than that. One can only do that in the space. They can't do it on the Earth. So,
Yeah. And you won't have actually 2.5 million kilometers arm length on Earth. So you want to go to space to get that. And so, and your sensitivity is dependent on the length of arm and how well your test mass is suspended.
both the noise and the arm length are important as
Yeah.
we pointed.
So yeah, I'm really sorry I couldn't get this to working.